y is in terms of x, and we have x bounds. So there's no change in a variable we need to do. Remember, for arc length, if it's in y, you have to make sure everything's in y, but if it's in x, make sure everything's in x. Here, everything's in x, we're good to go. We're going to call this our function, though. So if y is by itself, we can replace y with f of x. So instead of saying y is equal to, I'll say f of x is equal to. And remember, the arc length formula is L is equal to the integral from a to b of the square root of 1 plus f prime squared dx. So our first thing we have to do here is find the derivative, then square it. So let's do that right here, off to the side. So the derivative of this is going to be, let's see, 2 times, So derivative of ln of something is derivative of the inside divided by the original inside. So all over sine of 1/2 x is going to be the derivative of sine of 1/2 x. Derivative of sine is cosine. Since it is of 1/2 x by chain rule, we have to multiply by 1/2 on the outside. So I don't know if we catch that, but I'm using this fact here. The derivative of ln of a function is the derivative of the inside divided by the inside. Because derivative of ln of x, let's say, is 1 over x, so derivative of ln of anything is 1 over that something, but then by chain rule, you have to multiply by derivative of the inside. So if you bring those together, you just get g prime over g. Okay. So I hope that's clear. Is that okay?
Yeah.
Okay, thank you. Now, of course, 1/2 times 2, you can bring the 1/2 outside of the fraction. There's a bunch of ways to see it, but in reality, what happens is this happens. The 2 and 1/2 cancel. And then when you square this, well, let me just say the following. In this case, sine of, I have to pass it through 2 times because how I'm using is too dry, too wet. But in this case, cosine over sine, hang on, let me see if there's a better way to
cotangent?
write it. It is cotangent. I guess that's okay. Well, that's fine. Let's see what happens. So it's going to be cotangent of 1/2 x. So if we take that into account, what we have on the inside here is radical 1 plus cotangent squared of 1/2 x dx. The integral will then be from where to where, just whatever the bounds are. In this case, it's pi over 3 to pi. So those are the bounds. Okay. The only issue is that can the inside be, well, it looks like it's trying to be a Pythagorean identity. Is there a Pythagorean identity for 1 plus cotangent? I believe there is. What we can do is we can just check. Well, here's what I'm going to do. So I'm just going to recall sine squared plus cosine squared is equal to 1. Now, how do I make one of these terms be cotangent squared?
The identity is cosecant squared of x, right?
Isn't it divide by sine squared?
Yeah, so if you divide by sine squared, yeah. If you divide by sine squared, that's what I was trying to get at. If you divide by sine squared in the Pythagorean identity we know, we get 1 plus cotangent squared is equal to cosecant squared. So all of this on the inside of the radical is just cosecant squared. So this becomes the square root of cosecant squared of 1/2 x. The square root and the square will cancel out. Oh, this is a nasty problem. But it's kind of doable. It's just we get a weird integral that we can do, but we just haven't really seen it too much. Well, we've seen it a little bit. We actually have seen it more than I'm used to. We get this. Okay. Now, if you didn't like how I did this, there's another way of doing it, and that's by leaving it as cosine over sine. If we had left the this as cotangent, well, you have to square it. So if we had left this cotangent squared as cosine squared over sine squared, we'd have to write 1 as sine squared over sine squared, and you would get
Wouldn't now we just turn it back to sine and cosine? I mean 1 over sine. Just change it back to sine.
No. To integrate this, there's a special integral that we can use.
Okay.
For cosecant, but I'll talk about that right now. What I was going to say was that if you don't like this being cotangent, you can rewrite it as cosine squared over sine squared, but then that 1 would be written as sine squared over sine squared, so that you have a common denominator, like this. Plus the cotangent squared, which is cosine squared over sine squared. And notice what happens. When you combine these, you get sine squared plus cosine squared, which is just 1. So in total, this will be 1 over sine squared anyways, which will still be cosecant squared. So if you don't see this identity right away, you can always rewrite it as fractions, combine with common denominators, and you'll get the result regardless. So I hope that makes sense. Now, the integral of cosecant, let me see how many people have joined us now. Okay, there's a few more, but still not too many. That's fine. There is actually a special integral, and the integral is, well, there's 2 that come to mind. The one that comes to mind is the integral of secant. So the integral of secant theta is ln of absolute value of secant plus tangent. I don't have space. Let me do that again. So, I'm not too much in the way here. Jeez, man. Ugh. There we go. So I hope we can all see that. But the integral of secant of theta d theta is ln of absolute value of secant theta plus tangent theta. So that's a special integral for secant. For cosecant, it's fairly similar. Remember, a trig function and its co-trig function have similar derivatives and antiderivatives. So for cosecant of theta, I'm pretty sure its antiderivative is negative ln of cosecant plus cotangent. It may be minus, but actually we can check this. Of course, really you could just use a table in the back of the book. So in the back of the book there are trig integral tables. But anyways, let me check. So derivative of ln of something is, remember, derivative of the top over the original denominator, the original inside. So the original inside is cosecant theta plus cotangent theta. Derivative of cosecant is, well, so remember, so it's kind of like a little bit circular logic. Derivative of secant is secant tangent. Derivative of cosecant is negative cosecant tangent, or negative cosecant cotangent. Derivative of cotangent squared, well, derivative of tangent squared is secant squared. Derivative of cotangent squared is negative cosecant squared. So notice on top, what they both have in common is cosecant. So if we pull out cosecant, what we have left on, well, actually we pull out negative cosecant. So if we pull out negative cosecant on the top, what we have left on the top is cotangent theta plus cosecant theta. And that will indeed actually cancel the denominator. So I'm going to get out of the way here to see if we can see that. Hope the quality is coming out okay. Hope I'm not writing too small.
I could read it.
Okay, thank you. Good. So you see what happens here? The fraction is just 1, so this is negative cosecant. And yeah, and all I've done here, this thing in parentheses is just the derivative of ln of that. I didn't even consider the negative on the outside. So if I consider the negative on the outside, then this would be negative that, which in total will just amount to positive cosecant squared. So I've taken the derivative of what I thought would be the antiderivative and got back the actual integrand, meaning that is the that's the antiderivative. Whew. Okay, so do we have space? I think we have space. Well, we kind of have space. I still have to erase some things though, because I could write it here, but then we still have to evaluate between the limits. So I'm going to erase a few things. Is that okay?
Yeah.
There's a little bit of a problem. The problem is that it is of 1/2 x. So technically we have to do a u sub here. So if we were to let the inside, let's say 1/2 x be equal to, I guess I could say u, but I'm going to call it theta just so we can see it more easily. If I were to let the inside be theta, then d theta is 1/2 dx. Okay, so to get dx by itself, we can multiply both sides by 2, so that 2 theta is equal to dx. So I'm kind of doing a u sub here just to show something. If we make this substitution, then this just becomes cosecant of theta d theta, but with a 2 on the outside. Okay. The antiderivative of cosecant of theta is this, where these are thetas instead of 1/2 x's. So basically what I'm saying is that all we need to do here to make this true is multiply by 2 on the outside. I hope that's kind of clear. This phenomenon is something that we've seen a lot in class, and I've always said this. If you have an integral of a function of a times x plus b, so if it's of a linear function, if the inside of the function is a linear expression, then this is always going to be 1 over a times the antiderivative of f evaluated at that linear function, and then plus c. So basically divide by the derivative of the inside. Since the derivative of the inside in this case is 1/2, dividing by 1/2 on the outside gives you 2. So that's something that is actually quite common that we've seen a lot, but maybe it's just been a while, I don't know. But yeah, that's all I'm going to say for that one. But if you do a u sub, you'll see that a 2 pops out. I'm just not being super specific with the details. So it's -2 times, doing the evaluation, let's see. We have ln of, sorry, this board is being a pain right now. Ln of absolute value of what? Well, it's going to be cosecant of the top one, so pi over 2. Plus cotangent of pi over 2. Well, I guess it's fine. I can just leave it like this, I guess. There we go. So this is the first thing, plug in pi. So when you plug in pi into this expression, you get this. Minus, when you plug in pi over 3, what do you get?
Pi over 6 for the...
You get pi over 6, exactly, because 1/2 times pi over 3 is pi over 6. So this is going to be minus, we're pulling out the -2, so we're just worried about the ln part. So I'm just looking at this. The -2 I already pulled out, so we don't need to worry about that when evaluating it for the next one. So that's ln of absolute value of cosecant of pi over 6 plus ln of, oh, sorry, not ln, cotangent, there we go. Cotangent of pi over 6. And then close brackets. Nice. We're good there? Hope we can see that. So now we need to figure out what these values are. What's cosecant of pi over 2? What's cotangent of pi over 2? Cosecant of pi over 6 and cotangent of pi over 6. Well, let's see. So cosecant of pi over 6. Oh, let's do pi over 2 first. Cosecant of pi over 2 is 1 over sine of pi over 2. Sine of pi over 2 is 1, so this is just 1 over 1. So it's just 1. So that's 1. Cotangent of pi over 2, I think, is also 1. No, I'm sorry.
0.
Cotangent of pi over 2 is 0, yeah. Cotangent of pi over 2 is 1 over tangent of pi over 2. Tangent of pi over 2 is undefined, but maybe a better way of thinking of it is like this. Cotangent is cosine over sine. Cosine of pi over 2 is 0, sine of pi over 2 is 1, so in total this is just going to be 0. Good. So that's 1, that's 0. And now let me take advantage of this space here. I'm going to erase the pi over 2s and write pi over 6 so we can see what's up for these values, for these two values. Okay? So I'm going to erase this.
Cool.
Well, actually, I'm just going to erase the 2. So it's pi over 6, pi over 6, pi over 6, and pi over 6. For a cotangent, it's probably best to write it as 1 over tangent. Maybe it'll be easier to see. But let's see. For the top one, what's sine of pi over 6? Sine of pi over 6 is 1/2. So this is 1 over 1/2, which is just 2. For cosine, so we know sine of pi over 6 is 1/2. Cosine of pi over 6 is radical 3 over 2. So if you multiply the top by the reciprocal of the bottom, the 2's cancel, and you just get radical 3. So cosecant will be 2, cotangent will be radical 3. Is that okay?
Yeah. First time will cancel out because it just becomes natural log of 1.
Exactly, yeah. So this is just going to be ln of 1 plus 0, so that's just ln of 1. And ln of 1 is 0, so I'll do that after the fact. And this is going to be ln of 2 plus radical 3. And the reason why I'm dropping the absolute values now is because each of these are positive numbers, and absolute value of a positive number is still that number. And yes, as it turns out, ln of 1 is 0. So all we're left with is negative 2 times negative ln, which is positive 2 times ln of 2 plus radical 3. And then you can approximate this if you want, but I'm not going to. Is that okay? Go from y equals 1 to y equals 3. All right. Oh, you know what? Now that I think about it, there's a problem on here that may be a typo. Ugh. Well, I hope it's not this one, but let's see. You know what? It may be this one. Oh, that's fine. So to get everything in terms of y, we have to get x completely by itself. So I'm going to divide everything by 12. Why do we want x by itself? Because if x is by itself, we can call it a function of y. Kind of like how when y is by itself, we call it a function of x, just with the other variable. So this is going to be 12 over 3. 4 over 12 is 1 over 3, y to the third. 3 over 12 is 1 over 4, y to the negative 1. I guess that's an okay way to write it. I was going to write it as 1 over 4y, but this works actually. So remember that our arc length formula calls for the derivative of this squared. So it's going to be L of integral, well, L is going to be equal to the integral from a to b of the square root of 1 plus the function squared. In this case, it's of y, and then that would be dy. It's the same equation, just with y's instead of x's. So now let's find the derivative of this, f prime of y, and then we'll square that. So let's see. When you take the derivative of this, the 3 comes down, so that'll be just y squared minus 1/4 y to the negative 2. Okay? 1/3 times 3 cancels out, and then the new power is 2. Negative 1 comes down, and then the new power is negative 2. Okay, so now when we square this, to find the derivative squared, by the way, like I said, I recall there being a typo on one of these. If there is, I'll do two things. I'll update the reviews to compensate for that typo, and if we can't figure it out right now live, then we'll skip it, and then I'll make a video for it later. But I think this should be okay now.
Cool.
So let's see. So when you square this out, the first one squared is y to the 4th. Their product is going to be negative 1/4. You see that? Because when you multiply y squared to y to the negative 2, they cancel, and then it's just going to be 1 times negative 1/4, which is negative 1/4. But remember how foiling works. It's the first one squared, 2 times their product. So it's going to be 2 times negative 1/4, which is negative 1/2, and then plus the last one squared, which is 1/16, y to the negative 4. So you FOIL it out, you'll get this. I know it's a lot to look at, but that's what we end up getting here. The real good news is that when you add 1 to it inside the radical, so we're going to do 1 plus what we just got, basically, inside of the radical, what happens? Well, what happens is the 1 and negative 1/2 will combine to positive 1/2. So when they combine to positive 1/2, it may not look like it's much, but what it actually does for us is it gives us the same thing we had before, only with a plus in the middle instead of a minus. So if this was a plus, then that would be a plus here. And this is something we actually saw in class. Well, oh, by the way, the bounds are 1 and 3. So what I'm trying to get at is this trinomial here really can be factored. And how we can witness it can be factored is that if you have a difference squared, it's the same as a sum squared, just with a middle sign change. So really I'm saying this. A plus b squared is a squared plus 2ab plus b squared. A minus b squared is a squared minus 2ab plus b squared. Right? So notice the bottom one here is what we got first. And then after adding 1, since 1 minus 1/2 is positive 1/2, we get the exact same thing only with a plus. So then we get the top version of it. So we can write the inside now as a square. We can write it as what squared? As y squared plus 1/4 y to the negative 2. And then dy. And now, of course, the radical and the square cancel out. And by the way, these are basically the only options as far as the integrals go for arc lengths. So what I mean by that is the following. For arc length problems, in order for them to actually be doable by hand, which is what you'll see in the exam, either it's going to involve some trig identity to cancel the radical, or it is going to involve this weird binomial switcheroo thing. So it's important to see the pattern here to know this. So I hope that's okay. If you don't quite see that, there is another way of doing it, where if you don't see that this is relatable to what we just did, which you should see that because we just did it, and we also saw this in class before. But again, if you're not comfortable with this, there's a way of doing it by writing it all as one fraction with a common denominator. You can square root the denominator, and that'll come out of the radical. That'll come out of the radical. And the top should be a little more obvious that you can factor it. Yeah, I kind of don't want to do it because it'll take too much time, but try it. Maybe you'll see what I mean. Anyways, I'm gonna have to erase some things. So I'm gonna erase everything over here to the right. Yes.
You give me a minute so I can.
Okay. Okay, no problem. So I know I kind of went all over the place, but I was going from. I know I don't have too much space too, but I went from here down and then here. Well, kind of. I went up to this point. So what I have cornered off here is just the explanation of how I knew to write this trinomial as this squared binomial.
Okay, you can go ahead. I took a picture.
Awesome, thank you. Yes, you can just screenshot at any given time. But yeah, I'm gonna erase. I always just try to give a good notice. So let me erase this part here. Okay. So the radical and the square cancel. So this is just the integral from 1 to 3 of y squared plus 1/4 y to the negative 2 dy. We did all of the hard part. This is easy now because they're powers of y. So the antiderivative of y squared is y to the 3rd over 3. The antiderivative of 1/4 y to the negative 2 is 1/4, let's see, y to the, add 1 to the power, negative 2 plus 1 is negative 1. And then when you divide by negative 1, it just changes the sign to negative. Right?
I have a question.
Yes.
I know you already erased it, but it was 1/3 over y cubed plus 1/4 y negative 1.
That's this, yeah.
Yeah, so how then y became y squared minus 1/4 y minus 2?
That was the derivative.
Oh.
So what's the derivative of 1/3 y cubed?
Did you cancel the 3 and then do the derivative over?
Yeah, exactly.
Okay.
Yeah, because when the 3 comes down, it cancels, and then you just have y squared.
Oh, just making sure.
Okay, no problem. Thank you for asking.
Thank you.
No problem. Good. So there we go. So we have that. And now we have to evaluate this between the values 1 and 3. What's really funny is that it's just the same function with a sign change in the middle. Anyways, plugging in 3 gives us 3 to the 3rd over 3 minus 1/4 3 to the negative 1 minus, when you plug in 1, you get 1 to the 3rd, which is just 1 over 3, minus 1/4 times 1 to the negative 1, which doesn't affect it. So we just have this now. Yeah, so this is kind of nice. So you can cancel these. This is just 27 over 3, which is 9. But you can think of this as 3 to the 1. 3 to the 3 over 3 to the 1 is just 3 squared, so that's 9. This, the second term, is going to be 1 over 12. Right, because 3 to the negative 1 is 1 over 3, and then 3 times 4 in the bottom is just 12. Okay. Minus, if you multiply this top and bottom by 4 and the second one top and bottom by 3, you get 4 minus 3 all over 12, which is 1. So it's 1 over 12. Okay. So they don't actually, the 1/12s don't cancel, unfortunately. I wish they would, but no, they don't. So what we end up getting is 9 minus 2/12, which is 1/6. So if you write 9 as 9 over 1 and get a common denominator there, provided I didn't make any mistakes, we're done. 9 times 6 is 54, so it's going to be 54 minus 1 is 53 all over 6. So if you recall the surface area formula, it is S is equal to 2 pi times the integral from our bounds, in this case it'd be 1 and 2, and then it's the function of x times the square root of 1 plus the function squared, the derivative of the function squared. But they're actually, this is for about the x-axis. And if you want about the y-axis, just change the x's to y's. That poses a huge problem here, though, because, well, we'd have to solve for x in terms of y, and that seems kind of difficult here. You'd have to complete the square, which is kind of doable, but we're not going to do it. Instead, there is a different version of the formula when it is about the y-axis. So let me just say this. And I've said this before in class, but I believe when I said it, it wasn't really obvious, and it wasn't, well, none of this is obvious. When I say this is obvious, it's not obvious, and it doesn't really help. But I said this once in class, and I don't know if the explanation was the greatest, but here it is. Someone just joined, I think. Let me just, oh, a few people joined. Good, good, good. Awesome. Okay, so f of x is y, so we have this. But this is about the x-axis. So that's, oh, sorry, the integral should be on the outside. Oh, sorry. There we go. So that's the formula, okay? All right, so notice there's a y on the outside. Something that I want to say is that this whole thing here, after the y, is actually equivalent to the square root of 1 plus dx over dy squared times dy. And I actually proved this in class, and it's because if you find a common denominator, you get, it's dx squared plus dy squared all over dx squared. If you square root dx squared in the denominator, the dx's cancel, and you just get radical dx squared plus dy squared. Same thing happens here, and you still get radical, well, it would be dy squared plus dx squared, but adding those in any order is the same. So they're equivalent. And this is about the x-axis. What that means is that if it was about the y-axis, well, this f of x would be f of y. Since f of x is y, f of y would just be x. Okay. So I don't know if we follow that or not, but basically, long story short, if you're rotating about the y-axis, all you need to do for your setup is just have there be an x in front of the radical. And that's it. So let's see. First off, we need to find the derivative, then square it. So, yikes. Yeah. Let me do that off to the side. So if this is our function of x, then what's f prime? So notice the 4 comes down. 4 over 16 is 1 over 4. The powers are reduced by 1, so instead of x to the 4th, it's x to the 3rd. This, I'm going to write this over here. This is plus 1/2 x to the negative 2. That's that second term as a power. So using the power rule, the negative 2 comes down, cancels this 1/2. So that'll be minus now x to the negative 1. Sorry, negative 3, because you subtract 1. There we go, like that. Okay, good. All right. Great. Now what? Well, now when you square this, you actually get a similar thing to what we had before. If you don't remember, what we had before for the arc length problem we just saw where we did that binomial thing, we had something like this. The powers of x's were the same, and one was 1/4 times the other. So let's see if we get something similar when we square this out. So when we square this out, the derivative squared is going to be what? It's going to be 1 over 16 x to the 6th. Okay. 2 times their product. The product will be, well, the x's cancel when you multiply them. So when you multiply them, the x's cancel, and you get negative 1/4. 2 times negative 1/4 is negative 1/2. And then plus the last one squared is x to the negative 6. There we go. Yes.
Let me get this right. When we squaring the derivative, we go by the formula a squared plus or minus 2ab plus b squared. That's what you're doing.
Yeah, exactly. Yeah, it's a plus b all squared. It's a squared plus 2ab plus b squared. But in the minus case, yeah, there's a minus in the middle sign.
All right.
The middle sign changes. Okay, good. So now this is 2 pi outside of the integral of, well, from 1 to 2, the bounds are 1 to 2, x times the square root of 1 plus the derivative squared, we just found it. It's this trinomial here. So let me write this out. 1 over 16 x to the negative 6, or I guess x to the positive 6, what I meant to say, minus 1 half plus x to the negative 6. So I'm going to pause here for a moment, and I want to see if we can all see what's happening. It's the same exact thing we saw from the previous problem. The 1 and negative 1 half combined to positive 1 half. You see that? And we end up getting this same thing with a plus, and we can factor it as this, all squared with a plus in the middle. So these two combine to give us this. We can write this as this. Everything else stays the same. So make sure I have everything else correct. 2 pi is still on the outside. The integral is still from 1 to 2, and these are all equal. Whew, nice. And then the radical and the square cancel. Great. After doing that, all we need to do is distribute the x in and then apply the power rule. Then evaluate. So I'm going to give you a little bit of time to write this down or take a screenshot, whatever you need to do. Then I'll erase it, lift this up, and then I'll solve the integral. So now, distributing the x, we get 1/4 x to the 4th plus x to the negative 2 dx. Integral from 1 to 2, 2 pi. We don't need the bottom anymore, so let me erase that. Great, so now we can antiderive. To antiderive this, you add 1 to the power and then divide by the new power. So it would be over 5, and it's multiplied by the 1/4 that's still there. Good? So really, this is x to the 5th over 20. Here, if you add 1 to the power, you get x to the negative 1, and dividing by negative 1 will give you negative x to the negative 1, or negative 1 over x. Okay? Now we're going to evaluate this expression between 1 and 2, and then multiply by 2 pi after the fact. So any constant multiple you can bring outside of the evaluation completely, and that's what I'm doing. So now plugging in 2 gives us 2 to the 5th over 20, 2 to the, well, I'll just write it out. 2 to the 5th over 20 minus 1 over 2, the first one, minus when you plug in 1, it's going to be 1 to the 5th over 20, which is just 1 over 20, and 1 over 1, which is just 1. Now, plugging in 1s and 0s are kind of the easier ones to do. When you plug in 1, all of the x's become 1, so you ignore powers, basically. What now? There are probably some nice, clever ways of handling this. Let me see. I'm going to try to do a few things. So first off, 2 to the 5th is 32. I'll distribute the negative. You could combine those, but I'm not going to do that yet because there's, I think that there may be some arithmetic that happens. So far, so good?
Yeah.
Okay, sorry, I thought someone had a, yeah. I was making sure everything's okay. Right, so negative 1/2 and 1 combine to positive 1/2 because 1 minus 1/2 is positive 1/2. And 32 over 20 minus 1 over 20 is 31 over 20. So this is going to be 2 pi outside of 31 over 20 plus 1/2. So you may have thought that I was going to reduce this to 16 over 10, or I guess you could divide by 4, so it'd be 8 over 5. But instead I'm going to keep it like this to combine with this one. That's what I don't want to fall into that trap there. That's why I distributed the negative. Good. And then we can multiply this by 10 top and bottom to get our common denominator of 20. So that's going to be 31 plus 10, which is 41 over 20. So in total, let me write it over here. Our answer will be 2 pi. Let me write this actually. That looks good. So 2 pi outside of what? 31 plus 10 is 41 over 20. The 20 and 2 pi cancel. So it's just 41 pi over 10. Whew, nice. That's the answer for the volume. Or not volume, it's surface area. That's the answer for the surface area. So I'm not writing the whole problem here, but this is a surface area rotation problem. We're rotating the curve y equals x squared from these 2 points above the x-axis. You can even visualize it if you want to get an actual image. Y equals x squared is a parabola, but going from 0 to 1 is just, I guess, this part of the parabola. So it kind of looks like a ramp. Rotating about the x-axis will give you this kind of cone shape. It's like a concave cone. And we're finding the surface area of this object. Of course, when I say surface area, I mean the surface area surrounding it. We're not finding the surface area of the endpoint, which is kind of interesting. So imagine it's like a horn. We're finding the surface area for the outside of the horn. So it's hollow, basically. Just wanted to say that. So now let's actually start the problem. And again, we'll use the surface area formula directly. And we're going to get s is equal to 2 pi outside of the integral from our bounds, 0 to 1, times the function x squared times the integral of 1 plus the derivative squared dx. Well, let's see. The derivative of x squared is 2x. So it's just this. Okay, I'm looking at this and I'm seeing a trig integral. So it looks harmless, but actually when doing it, when actually evaluating the integral, I think we need to do a trig integral actually. Let's see. Let's see why I see it. Let's see how I can see that. Maybe we can figure that out. How I can see that is, well, first off, u sub doesn't work. If the inside is equal to u, then du would be 8x, but this is x squared, and it doesn't quite catch that exactly. So it's x squared, not x. If it was x, then you can just divide by 8, basically. Yeah, but it doesn't quite work in this case. So there may be other ways of doing it. You can try by parts if you like, but I'm not even going to risk it. I'm just going to go straight for a trig sum. So with that being said, this is a plus. It reminds me of 1 plus tangent. So if this was only tangent theta, if that was tangent squared theta, then we would be set. Yeah. So in fact, you know what? Looking back at this, if 2x is tangent theta, then that means 4x squared is tangent squared theta. Now I remember someone saying for the first exam, this is a kind of trap they fell into. They let the inside itself be that squared, or the whole thing be that squared. Don't do that. So if you were to write for yourself, if you were to write 4x squared equals tangent squared, it's going to be a mess. It's best to let 2x equal tangent so we don't have squares in our substitution. So here's what I mean by that. So our substitution is going to look a little funny. It's going to be this. It's going to be 2x equals tangent theta. Really what we're doing is we're letting x be 1/2 tangent theta. So that when you square 1/2 tangent theta, you get 1/4 tangent theta squared, and the 1/4 cancel, and we just get 1 plus tangent squared, which is what we want. But this is another way of doing that. So now if you take derivative of both sides, derivative of 2x is 2dx. Derivative of tangent is secant squared theta, d theta. And we actually have 2dx. Look at that. We have 2dx. There's a 2 and there's a dx. The 2's on the outside, but constants can be pulled on the inside, so that's fine. So I'll replace 2dx with, let's see, with d theta, with a secant squared d theta. All right, so far so good, but we have that x squared. Remember, x is going to be 1/2 tangent. So if you actually solve for x, well, that's fine. If you actually solve for x, you get 1/2 tangent. So this is going to be 1/2 tangent all squared. On the inside, this is going to be 1 plus 2x is tangent. 2x squared is 4x squared, so that's just going to be tangent squared just like we want. Hope this isn't too much to follow. 1 plus tangent squared is just secant squared. And notice the radical, so I'm going to replace this with secant squared. The radical and the square cancel. So in total, we're left with the following. I'm going to write it out and try to simplify a little bit, and let's see if we can follow and get what I get. So in total, I get this. Pi over 4 tangent squared secant cubed. You all see that? Well, tangent cubed I think we see because this part, after canceling the radical with the square, which is secant times secant squared is just secant cubed, adding the powers. Okay. How do I get this pi over 4? Well, when you square this, you get 1/4 tangent squared, and 1/4 times pi is just pi over 4. The only issue I have now is I have to change the limits because these are x values. So when x is 1, if you plug x equals 1 into our equation, into our substitution, in fact, we can even use this one here. When x is 1, we get 1 is equal to 1/2 tangent theta. Multiplying by 2 gives you 2 is equal to tangent theta. So that means theta is tangent inverse of 2. Let me write that one more space. Which is a terrible value, honestly. Tangent inverse of 2 is not a special value. So that's kind of unfortunate. Let's see what happens with 0. So when x is equal to 0, what do we get? Well, using this equation, we get 0 is equal to 1/2 tangent of theta. Multiplying by 2 gives us tangent of theta is equal to 0. That's actually okay because tangent of 0 is 0, so that means theta would be 0 to give tangent of theta being 0. So 0 will still correspond to 0, but 1 will correspond to tangent inverse of 2, which is yikes. But we'll handle that in due time, I guess. All right, so for number 4, as we did it, there's good news and bad news. It's kind of all bad news. But we have to use these special integrals, basically. The integral of secant cubed and the integral of secant to the 5th. So it's definitely doable. I don't know if you quite want to see me go through the pain of doing this, but we definitely can do it. I don't think it's really going to be worth it because you won't have anything this complicated on the exam. And, well, I kind of don't want to do it, but let me just start it off just to show you, to get an idea. So we know tangent squared is secant squared minus 1. So after distributing secant cubed, take theta, and that's still the same. Limits are the same, that's still the same. This is going to be secant to the fifth minus secant to the third. And the integral of each of these are given there. So yeah, you can just do top minus bottom, I guess. It's really gross, obviously. There's 3/8 minus 1/2. 1/2 is 4/8. So 3/8 minus 4/8 is negative 1/8. So we're going to get negative 1/8. Well, I guess we could write it in order. So it's going to be 1/4 tangent. There's a theta missing there. So tangent theta, secant cube theta, and then I have for the secant tangents, I have 3/8 minus 1/2, which we already said was negative 1/8. That's tangent theta, secant theta, and then minus 1/8 ln of secant theta plus tangent theta. Whew, nice. Now all we have to do really is just evaluate between the limits. And yeah, there's even more work to do here, and then multiply by pi over 4 on the outside. And yeah, again, there's a little more work to do here because, well, plugging in a 0 won't be too bad. In fact, I'll tell you right now, when you plug in 0, that's 0, that's 0, that's going to be 0, that's 1, but ln of 1 is 0, so plugging in 0 will give you 0, actually. Okay, good. And this is, of course, because a tangent of 0 is 0. When you plug in tangent inverse of 2, well, all of the tangents will turn into 2. Secant, though, what is secant? Well, let's try to figure that out here. So if we call this our theta value, then that means tangent of theta is equal to 2. So if tangent of theta is 2, this is the triangle we have. That's a triangle with angle theta. Tangent is opposite over adjacent, so it's going to be 2/1. This would have to be, well, I guess this squared plus this squared, so it's going to be radical 5. If I'm doing that correctly. Well, I'm just going to go with it, but yeah, okay. So now what's secant? Secant of theta then is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant is going to be hypotenuse over adjacent, which is just radical 5. So everywhere we see a tangent, tangent of tangent inverse of 2 will be 2. So all of these will turn into 2's. It's actually not too bad, actually. I guess the only real bad news is that we have to be given these formula here, which they're kind of in the back of the book. We have to do a little work to get to them. We have seen secant cubed in class, though, once. Secant to the fifth we haven't seen, though. So that, yeah, that's crazy. So tangent will be 2 when you plug in tangent inverse of 2. And secant will be radical 5. Now be careful, this is secant to the third. So that's going to be radical 5 cubed, which is radical 5 times radical 5 times radical 5. Of course, 2 radical 5s just give you a 5. So this is 5 radical 5. Good. So we're practically done then. Just plug and chug. So we get 2/4, which is 1/2. Let me write it like this. 5 radical 5 over 8. Over 2 is what I meant to say. 2/4 is 1/2. There we go. Good. Minus, that's going to be radical 5 over 4. Minus, this is going to be 1/8 ln of, let's write it as 2 plus radical 5. And then the whole thing is multiplied by pi over 4. And yeah, that's the furthest I'm going to take this. I'm going to call this a win. But yeah, like I said, this is way, way, way too difficult to be on the exam, just because of those mainly. But aside from that, it wasn't too difficult. Hope you enjoyed that. Now moving on with the review. So the region bounded by these two. So remember how that works. If you don't remember how that works, the centroid is the following. So the centroid is going to be the point, so the centroid C is the point x bar comma y bar, where x bar is 1 over the area between the curves. times the integral between the bounds. Right. So it's the top function minus the bottom function. I thought it was the other way. I thought it was the square, but the squaring one is for the y, I guess. So there's a 1/2 in front of this, like I thought there would be. That's just from the formula. So let's see if we can find this. The only thing, though, is that we need to find first, we need to find A, the area. And then second, we need to find out which one the top one is and which one the bottom one is. So there's a little bit of work to do. So the good news is that the area, if you don't remember, is just the integral between the bounds of the difference between the two functions. And it doesn't matter which one's on top and bottom because we can just take the absolute value at the end. Because area will always be positive. X bar and Y bar may not be, but the area will indeed always be positive. So what are the bounds? So to even find the bounds, we have to set these equal to each other. So let's do that. So 1/2 x is equal to radical x. If you square both sides, you get 1/4 x squared is equal to x. And if you multiply, I guess, both sides by, there's a few ways of doing this. But if you multiply both sides by 4 and subtract, you get x squared is equal to 4x. X squared minus 4x is equal to 0. There's a few ways you could do that, but this is one way of doing it. Factor out x, you get x minus 4 all times x. So then applying the zero product property, you get either x is equal to 0 or 4 by setting each of these factors equal to 0. So those are the bounds, 0 and 4. You can also graph it to visualize that too. And for, so for the area, it's just top minus bottom. We don't know which one top and bottom is, so we're just going to guess. So I'm going to do 1/2 x minus radical x. Remember, radical x is x to the 1/2, so it's easier to integrate. Antiderivative of this is going to be 1/2 x squared over 2. Antiderivative of this is going to be x to the 3/2 divided by 3/2. So remember, when you divide by a fraction, you can just multiply by its reciprocal instead. Good. Then evaluate between limits. Let me just separate these. So far, so good? Okay. Plugging in 4. So this is 4 squared over 4. Minus plugging in 4 also. So it's going to be 2/3, 4 to the 3/2. That's the first evaluation. And what happens when you plug in 0?
It's going to cancel it all out.
They all cancel. You get 0. They're powers of x. 0 to any power is 0. So that's going to be 0 for the first one minus 0 for the second one. So basically plugging in 0 doesn't do anything. This gives you 0 in your second term. You have to check, though, because it may not always be 0, but in this case it is. Okay, 4 squared is 16 over 4 is 4, minus 2/3 times 4 to the 3/2. So 4 to the 3/2, if you don't remember, that means the square root of 4 to the 3rd. So the over 2 part of the fraction power means radical. So that's 2 to the 3rd, which is 8. So this is that times 8, and that's 4 minus 16 over 3. 4 is 4 over 1. And if you get a common denominator, multiply top and bottom by 3, it becomes 12 over 3. And that's negative 4 over 3. Aha. So that means we guessed incorrect. So what that means is the first one is really the bottom function. And the second one is really the top function. Good. So now we know which one top and bottom is, and we know the area is going to be positive this. So remember, area is always positive. So in reality, since we guessed incorrectly, that means we really did it the other way around, and we have to take absolute value of all of this. So really, our answer is just positive 4/3 for the area. So we've only done 1/3 of the problem. 1 over a is going to be 3 over 4. So x bar is going to be 3 over 4. times the integral from the same bounds, 0 and 4. So maybe I should write that somewhere. Well, that's fine. We know the bounds are 0 and 4. And it's going to be x outside of the top one, radical x, minus the bottom one, 1/2 x. Okay, perfect. All we need to do here is just distribute this, antiderive, and then plug in. So that's not going to be too bad, I don't think. Let's see. So that's going to be x to the 3/2 minus 1/2 x squared. Dx. Integral between 0 and 4 still. 3/4 on the outside still. So far, so good.
Yeah.
If at any point you don't see how I got from one step to the next, let me know. I'm just going to carry on. So the antiderivative of x to the 3/2 is x to the 5/2 times 2/5 because I'm adding 1 to the power and then dividing by that. So when you add 1 to the power, remember 3/2 plus 1 is 5/2, and then dividing by 5/2 is just multiplying by 2/5. Minus, add 1 to the power here, we get x to the 3rd. Dividing by 3, what was it?
1/6.
1/6. Yeah, dividing by 3 will give us 1/6. 1/2 times 1/3 is 1/6. Good, thank you. And then evaluating this between 0 and 4. 3/4 is still on the outside of this evaluation, though. Now, good news again, what happens when you plug in 0?
Everything turns to 0.
Everything turns to 0, so we don't even need that one. We only need 4 now. So plugging in 4, here's what we get. We get 3/4 on the outside. Good. 2/5, 4 to the 5/2, minus 1/6, 4 to the 3rd. That's it. So 4 to the 5/2, remember, 4 to the 1/2 is radical 4. So we can actually get rid of the half on the bottom and the 4 by square rooting 4. So that's 2. So 2 to the 5th is 32. Okay. 4 to the 3rd is 64. 64 over, let me write it like this. 64, let me write it above like that. So 4 to the 3rd is 64. 64 over 6 is 32 over 3. Okay, so in total, here's what we have. 3/4 outside of 32 times 2/5 is 64 over 5 minus 32 over 3. Okay, there are actually a lot of ways we can evaluate this. Let me do the following. I'm going to notice that 64 and 32 can both be divided by 32, so I'll pull 32 on the outside. So that's 3 over 4 times 32 times what? So pulling 32 out gives us 2 over 5 minus 1 over 3. It just makes it a little easier to do the evaluation. Now, 32 over 4 is 8, so this is really 8 times 3 on the outside. So that's 24. Now, this inside, we can actually just find a common denominator. In fact, we can do this cross multiplication thing and get 2 times 3 minus 5 times 1 all over 5 times 3. But I'm just going to write it like this. So multiplying this top and bottom by 3, multiplying this top and bottom by 5. So we end up getting 6 minus 5 all over 15. That's just 1 over 15. And then we can cross cancel by dividing by 3. And we just get 8 over 5. So x bar is 8 over 5. Okay, so y bar. Good. Y bar is 1 over a, so that's 3 over 4 still. Integral from our bounds, 0 and 4. 1/2 on the outside according to the setup. Top squared minus bottom squared. Remember, our top is this. So it's radical x squared minus 1/2 x all squared.
Well, that makes it a lot easier.
Dx. It then makes it a lot easier, right? Because then the radical goes away. I agree. Thank you. Good. So the radical and square cancel. You just get x. So we get 1/2 outside of x minus, when you square this, you get 1/4 x squared.
Since the half's a constant, you can pull that out as well.
You can pull the constant out. I agree. Yeah, pull the constant out. You know, let me do that actually right away. We get 3/8. You all see that? You can just see multiplying these together because the constant can be pulled out of the integral. Good. So it's 0 to 4 still. Then we can antiderive each of these. Antiderivative of x squared is x2/2. Antiderivative of x to the second is x to the 3/3. The 1/4 is just hanging out there. Then we can evaluate this between 0 and 4 before multiplying by the constant on the outside. Whew. Good. And again, since they're powers of x's, when you plug in 0, you get 0. So we don't even need that. Plugging in 4 gives us 4^2 minus 4^12, because 4 times 3 is just 12 here. And then on the outside, we still have that 3/8 just lingering, waiting for us. There's a lot of cancellation here. A lot of cool things happen. Let's see what we can make happen. So this is 16/2. That's just 8.
Mm-hmm.
So it's 3/8.
This equals 1.
8 minus, okay, good. This is 64/12. 64/12, let me write it over here. You can divide top and bottom by 4. Top divided by 4 is 16. Bottom divided by 4 is 3. Okay? There's even better news. If you distribute this, you get like cancellation everywhere. So you get 3/8 times 8 minus 3/8 times 16/3. You see all the great cancellation?
Oh, yeah.
The 8's cancel, we just get 3. The 3's cancel, the 16 and 8 even cancel. Okay, so I got 8/5 for x bar, 1 for y bar. So our centroid is just x bar, comma y bar. All right, so moving on with number 5 from the review, find the centroid for, this is part B, the region that is bounded by these curves. Now, I'm going to actually take advantage of graphing these, and I'm going to show you a few things. So first off, y=0 is just the x-axis, so that's the bottom curve really. Sine of x will look like this, but we're going from pi/4 to 3pi/4. Now, this is 0 and pi, and then the next one is pi/2. Or is it? No, yeah, it's like this. Good. So 3pi/4 is going to be somewhere over here, and pi/4 is going to be somewhere over here. So that's pi/4, and that's 3pi/4. So really the shaded region we're looking at that we want to find the centroid of is this region. Below sine of x, above y=0, and then in between those x values. Good. So now the first thing we need to do is find the area. So that's the first step here. So the area of the shaded region is going to be, well, the integral between the x values of top function minus bottom function, so it's just sine of x really. Antiderivative of sine of x is negative cosine of x, and then just evaluate between the limits. Perfect. So plug in the top one. Let's see, what is negative cosine of 3pi/4? Well, cosine of pi/4 is radical 2/2. Cosine is negative in the second quadrant. 3pi/4 is in the second quadrant. So negative cosine is going to be, well, let me just say this. Cosine of 3pi/4 is negative radical 2/2. So the whole thing will amount to positive radical 2/2. That's for the first evaluation though. Then minus negative cosine of pi/4. This is radical 2/2. Positive radical 2/2. Double negative is positive, so we gain a plus radical 2/2. Since 1/2 plus 1/2 is just 1, radical 2/2 plus radical 2/2 is just radical 2. Basically, you get radical 2 plus radical 2 is 2 radical 2/2, the 2's cancel. So this is a limits pi over 4 and 3 pi over 4 of x times the top function times x minus the bottom function. Since the bottom function is 0, we don't even need it. So it's really just x sine of x. And yeah, this requires by parts. So I'm going to use tabular method here actually. So x times sine of x, derivative and antiderivative columns. Derivative of x is 1, derivative of that is 0. Now antiderive sine until we meet up to this 0. Antiderivative of sine is negative cosine. Good. Antiderivative of negative cosine is a negative sine. So multiply these and change the signs accordingly. So we end up with negative x cosine of x plus sine of x. And now what we have to do is evaluate this between limits pi over 4 and 3 pi over 4. And then multiply by 1 over the area, which by the way was 1 over radical 2, just to remind us. Okay, when we plug in 3 pi over 4, we get negative 3 pi over 4 times cosine of 3 pi over 4, which is negative radical 2 over 2, plus sine of 3 pi over 4 is actually positive radical 2 over 2, because sine is positive in the second quadrant and 3 pi over 4 is in the second quadrant. Okay, minus, when you plug in pi over 4, you get negative pi over 4 times cosine of pi over 4 is positive radical 2 over 2. Okay, plus sine of pi over 4 is just radical 2 over 2 again. And now multiply this whole thing by 1 over radical 2. There's a lot of things to combine, so let's see if we can figure that out. So this is going to be positive 3 pi radical 2 all over 8 plus radical 2 over 2. Distribute this negative and combine some things. This is positive pi radical 2 over 8 minus radical 2 over 2. Now the real awesome thing here is that since we're dividing by 1 over radical, we're dividing by radical 2, everything that has radical 2 on top cancels out, which is everything. So you basically ignore the radical 2's in the numerators and replace them with 1s, imagine. So notice 1 over 2 minus 1 over 2 cancel, and 3 pi over 8 plus pi over 8 is 4 pi over 8. 4 pi over 8 is just pi over 2. So x bar is just pi over 2. Wow, that was really cool. A lot of nice cancellation there. And now moving on to y bar. Okay, so now let us recall the formula for y bar. Y bar is, again, 1 over the area, but now times the integral between the bounds still, same bounds, same limits, of 1/2 times the function squared. It's really the difference of the function squared. So it would be sine squared minus 0 squared, but again, 0 squared we don't care about because it's 0. So it's just 1/2 is sine squared. And this also takes a little bit of work, kind of like the other one required by parts. This one, we've seen this a lot actually, before. We saw it in chapter 7 a lot anyways. This will require a half angle formula, or power reducing formula is what we called it. But yeah, so I'll pull out the 1 over 2, and notice this is, the area is 1 over, the area is radical 2, so it's 1 over radical 2. So pull out the 2 gives you this. Okay, integral between the limits still. And I'm going to use that power reducing formula I was talking about. So it's sine squared of x is equal to 1/2, 1 minus cosine of 2x. When it was cosine squared, it would be the same thing but with a plus cosine. So just keep that in mind. So to use this, I'm going to pull the 1/2 out. So this is actually going to be 4 because 2 times 2 is 4, of course. And that's going to be 1 minus cosine of 2x dx. Great. Antiderivative of 1 is just x. Antiderivative of cosine is positive sine. Since it's of 2x, you divide by 2 on the outside. Now I say positive sign, but since the sign's already negative, it doesn't change. Then we evaluate this between our limits. Pi over 4 and 3 pi over 4. Okay, and then multiply by 4 radical 2 after the fact. So let's see if we can do that now. So plugging in the top limit, we get 3 pi over 4 minus 1/2 sine of, let's see, 2 times 3 pi over 4 is, I guess, 3 pi over 2. So it's sine of 3 pi over 2. Sine of any pi over 2 is either positive 1 or negative 1. And sine of 3 pi over 2 is actually negative 1, as it turns out. Okay, that was the first evaluation. Minus, for the second evaluation, plug in pi over 4 into x, we get pi over 4, minus 1/2 sine of 2 times pi over 4 is pi over 2. And sine of pi over 2 is positive 1. Nice. So, okay, we'll distribute this negative here. Yeah, so I'm going to simplify this a whole lot. So I got 1 over 4 radical 2 times, we got 3 pi over 4, that's going to be, altogether this is positive 1/2, minus pi over 4. Okay, hope you're with me still. And then this is negative 1/2, but then with the negative distributed, it's positive 1/2. So these two will combine to 1. These two combine to, let's see, 3 minus 1 is 2, so it's 2 pi over 4 is pi over 2. So this is 1 over 4 radical 2 times pi over 2 plus 1. There are probably nicer ways of writing this. I could actually think of a few. You can combine into one common denominator, perhaps, as well. Yeah, I'm not going to do that, though. I'll just leave it like this. So it's 1 over 4 radical 2 times the quantity pi over 2 plus 1. I'm doing this kind of fast. I really hope there are no mistakes, but it's the work is definitely there. Right. I'm just not taking my time to check myself, really. But anyways, our answer is x bar y bar. So I guess I'll just write our answer then. So the centroid would be, let me write it over here, I guess. Pi over 2, comma, 1 over 4 radical 2 times pi over 2 plus 1. Perfect. So that was 5B, and now again, moving on with the review. So can we check this? We can check this by plugging it in. Also, it should say y equals, right? It should say is y equals this a solution. So I'll try to fix that typo as well as the other typo we saw. But yeah, to see if this is a solution, we have to find its derivatives to check the left-hand side and right-hand side. So let's do that. Y prime is going to be, well, let's see, that's going to be, if a is a constant, derivative of e to the negative ax is negative e to the negative ax. So I don't know if we see that or not, but basically, derivative of e to anything is itself times derivative of the inside. Since the derivative of the power is -1, a negative comes out. Derivative of b is 0 because b is a constant. Derivative of 1/3 x cubed, we saw that earlier actually. The 3 comes out and cancels the 1/3. So we get negative x squared. Similarly here, derivative of x squared is 2x. That cancels the 2 and just gives us 3x. Derivative of 3x is just 3. So far, so good? Okay, so now second derivative, very similar thing happens with the first term. It's itself, but then times by chain rule a -1 again. So double negative is positive, so that's just a e to the negative x. Derivative of x squared is 2x. Derivative of 3x is 3, and there we go. So now we're going to check the left-hand side. If the left-hand side combines to give us x minus x squared, we're done. The answer is yes. If it's not quite that, maybe there's some manipulation to make it the case, but chances are it's going to be no. Let's check. So we want to do y double prime minus y prime. So that's a e to the negative x minus 2x plus 3 minus y prime is going to be negative a e to the negative x minus x squared plus 3x minus 3. And already I can tell the answer is going to be no. You see that? Because after distributing the negative, I'm trying to see if I'm reading the question correctly. Yeah. So after distributing the negative, we get ae to the negative x minus 2x plus 3 plus ae to the negative x plus x squared minus 3x plus 3. So in total, we'll get this, 2ae to the negative x. These two combine to negative 5x. These two combine to 6. And then we have plus x squared. So this is the left-hand side, and this is certainly not equal to x minus x squared. I will say this, though. If it was plus, maybe that's what I meant to put. If it was y double prime plus y prime, then, well, then there's no sign change, and the ae to the negative x's would cancel. The 3's would cancel. We would be left with negative 2x plus 3x, which is x, and then minus x squared. So it would be x minus x squared if this was a plus. So the answer is no. And though it won't be a part of the question, just so we know it, it would be if it was a plus. So yes, if y double prime plus y prime. But that's just a side note. You don't need to write anything like that for the actual exam. So part B is a wash then. But I guess what we can do, so maybe this is another typo, depending on how you want to see it. You could either see it as, oh, the answer is no, so don't do part B. That's fine. But now B says, just to read this, as if part A is true, what values of A and B satisfy the initial condition y of 0 equals 1, y prime of 0 equals 0. So just so I don't leave you hanging on that part so you know how it's done, let's do B, assuming that it's y double prime plus y prime. Again, assuming it's this, B is skipped. But assuming it's plus, it would be yes, so we can continue and move on to part B. So I'm going to do a 6-star B, and I may change the review for that, but I'll erase this. Okay, so 6-star, if it's a plus, then the answer to A is yes. We saw that earlier. You get cancellation of nice things, of terms and things come nicely, combined to x minus x squared. So now we can move on to B for that. Otherwise, for 6, B is skipped. So it says, what values of A and B satisfy the initial conditions? Y of 0 is 1 and y prime of 0. So y of 0 is 1 and y prime of 0 is 0. So our solution, according to part A, was ae to the negative x plus b minus 1/3 x cubed plus 3/2 x squared. Sorry for continuing to go down like that. Just trying to see I have it written down correctly. Minus 3x. All right, so we need to find A and B by using our initial conditions. Now notice, this initial condition is good to go. We can just plug in 0, and then we can find A and B. There's a little bit of a problem, though. If we do that, you can actually solve for A and B. You'll get like A plus B equals something. But with that being said, let's find the derivative and see if we can at least apply this one. So the derivative, I gave it to you earlier, but I've erased it since, is, let me just do it quickly in my head, this. That's y prime. Y prime. So then y prime of 0 is then what? Replacing all x's with 0. So it's negative ae to the negative 0 minus 0 squared plus 3 times 0 minus 3. E to the 0 is 1, so that's just negative a minus 3, because negative 3 is still there. And what's y prime of 0? It's 0. That's what this says. So if you add 3 to the other side, or better yet, add a to the other side, then right away we get a is equal to negative 3. Very good. So now we use the second initial condition. Now let's use the first one. Okay, so y of 0 is equal to 1. So let's see if we can apply our initial condition there. Y of 0 is a e to the negative 0 plus b minus 1/3 times 0 cubed plus 3/2 times 0 squared minus 3 times 0. So everything with an x just turns to 0. And e to the 0 is just 1. So y of 0, which is 1, is just equal to a plus b. Since a is negative 3, this is 1 is equal to negative 3 plus b. So then adding 3 to the other side just gives us a b is 4. So that's the answer for part B. So this looks a lot like an integrating factor problem. It's not, though. And it's a little hard to tell because we have r's and t's. If you're not used to r's and t's, you can replace them all with x's and y's. And if you do, you'll get this. So if you replace all r's with y's and t's with x's, you get dy over dx, which is y prime, plus 2xy is equal to y. So you see why this is not an integrating factor problem? Integrating factor problems are of the form y prime plus p of xy is equal to q of x. But y is not a function of x, it's a function of y. So this actually doesn't work. In fact, if you subtract this to the other side, you get this. If you factor y out here, then this is actually an integrating factor problem. And you can apply the integrating factor formula. You can find the integrating factor I of x. But there's actually another way of doing it as well. And I mentioned this at the very, very end of last time. I believe like 1 or 2 people stuck around and asked a very good question. And that's, when can you do, so I said some integrating factor problems are separable. And the question was, when are they separable? And the answer, long story short, basically is they're separable when it's 0 on the other side. Because when it's 0 on the other side, you can just add it to the other side and then separate variables. So that's what actually I'm going to do here. So if you wanted to do this the integrating factor way, it's easier on the i's if you replace r's with y and t's with x's. Okay? But I'm not going to do it that way. I'm going to instead try to separate this. So we get dr dt is equal to r minus 2tr. So I'm subtracting this to the other side so that we can factor out r. And now we can separate the variable. Good. So multiply t to the dt to the other side. That's 1 minus 2t dt, like that. Divide r to the other side. We get 1 over r dr. And then integrate both sides. Integral of 1 over r dr is ln of r. And remember, we don't need absolute values for differential equation problems. Integral of 1 minus 2t is t minus t squared plus a constant. I did that kind of fast, but antiderivative of 1 is just the variable, so it's t. Antiderivative of 2t is 2t squared over 2. The 2's cancel, and you just get t squared. Also, derivative of t squared is 2t, so you can check by going backwards. Hope that's okay.
Yeah.
Now, to get rid of the ln, what do we do?
E.
E, yes. We take both sides as powers of e. So we get e to this. Well, on the left, they cancel. You just get r. On the right, this plus c part, if you remember, we can always write it as times e to the c. So e to the something plus something is e to the first one times e to the second one. So I'm splitting up sums of powers of e as products of those powers with those power, e to those powers. Only for c though, because why? Because what's e to the c? It's a constant. So we'll call it c. So that means this is c times e to the t minus t squared. Now this would be the answer. Of course, it's r as a function of t. this would be the answer, but we have our initial condition we need to apply. So if we apply our initial condition, remember this is R of t, then R of 0 is just c times e to the 0 minus 0 squared, which is e to the 0. E to the 0 is 1. So we just get R of 0 is equal to c. Well, what's R of 0?
5.
5. So c is equal to 5. So our answer is R of t is equal to 5 e to the t minus t squared. I would show you the integrating factor way of doing it, but I just don't want to spend too much time on it. So I'm going to move on to number 8. Okay, good. This is totally separable. Why? Because it's something equals something, they're products. Y prime is just what?
dy over dx.
dy over dx.
Y over dx.
Yeah, so that's the thing. For separable, we like dy over dx. For integrating factor, we like y prime better. But that was just me being picky. But anyways, for separable, let's cross multiply and cross divide. So dx is going to get multiplied to this side. On the right, we're going to keep which one? Sine of x.
Sine of x.
We're keeping sine of x because it has an x. Okay? And on this side, we have to divide by this because it involves x. So I'll divide by 1 plus cosine of x. Okay? On the left, there's dy after multiplying dx. And we're going to have to divide by this. So it's going to be 1 over 1 plus e to the negative y. Now we're going to integrate, right? Okay, this one is definitely a u sub problem. If we let u equal to the bottom, 1 plus cosine of x, du is negative sine of x, dx. Which is good because we have sine of x dx on the top to catch a part of this. Not all of it, but a part of it. So in fact, what we can say is negative du is equal to sine of x dx. And now what we need to do is replace what I circled in red here with negative du. So in essence, we get negative integral of 1 over u du. So you can check me on that, but that's what you get over there on the right. On the left now, I think it's a little trickier. It's tricky because there's no e to the negative y on top. But I think it's still doable. Let me see if there's a typo here or not. So also we'll try a u sub. So we'll let u equal 1 plus e to the negative y. That means du is going to be what? It's going to be negative e to the negative y. Derivative of 1 is 0. Derivative of e to the negative y is negative e to the negative y. dy. Now notice there's no e to the negative y dy here. There's only dy. The good news, though, is you can actually, if you look at this, it's not super obvious. Okay. So here, e to the negative y you can solve for by subtracting 1 to the other side. So that means this du is negative u minus 1 dy. So if you solve for dy will be 1 over, if you distribute this, this is just 1 minus u. So it's 1 minus u. So it's a little tricky, but that's our substitution. So dy is, and I forgot the du, didn't I? So dy is equal to this, and we have u still. So it's going to be the following. It's going to be the integral of 1 over u, because our denominator is u, times dy, which is 1 over 1 minus u du. This is this. Oh, by the way, these u's are not the same. They're different. So we have to kind of keep their corresponding substitutions. The antiderivative of 1 over u is ln of u. And again, we don't need the absolute values to throw us off too much. You only need to write plus c on one side of the equation for separable, so I'll write plus c on this side, not on this side, after integrating. Now remember, what's u?
1 plus.
Yeah, u is 1 plus cosine. Thank you. So it's ln of 1 plus cosine of x. And then plus our constant c. Yeah, the denominator can be factored, so you can actually write this as a over u plus b over 1 minus u. If you cross multiply to get a common denominator, you get a times 1 minus u plus b times u all over u times 1 minus u. And you want the top to amount to 1. In fact, what you can do is just let this equal 1. So if you let a times 1 minus u plus bu equal to 1, let me just make some space here. If u is 1, then the a term cancels and you just get b is equal to 1. If u is 0, then vice versa, the b term cancels and you just get a times 1 minus 0, which is a, is also equal to 1. Good. In fact, I kind of wanted to say it. If a and b are 1 and you just kind of cross multiply, then you get 1 minus u plus u, the u cancel, and you just get 1. So it's kind of funny to see. Okay, good. So antiderivative of 1 over u is ln of u. What's the antiderivative of 1 over 1 minus u? It's linear, right? 1 minus u is linear. Its derivative is negative 1. So that means that this is going to be negative ln of 1 minus u. So it's going to be ln of the bottom, ln of the denominator, but you have to divide by the derivative of the inside. Derivative of the inside is negative 1, so we divide by negative 1, so that plus becomes a minus.
Okay.
That's really what's happening there. Why we divide by derivative of the inside is because the inside is linear. So when you have 1 over a linear thing, you could just jump to ln. Or otherwise, you could just do another u sub if you want. You can let w equal 1 minus u, and then you get ln of w, but if 1 minus u is w, then dw is negative du, so a negative gets pulled out. So, yeah, that happens. But now, what's ln of u? Well, first off, we can combine them to ln of u over 1 minus u. Good. There's like even more trickery we can do here, but that's fine. So here's what I'm going to do. This is ln of u is 1 plus e to the negative y over 1 minus u. So 1 minus u, in fact, if you look at this, this is u minus 1.
Yeah.
If you negate both sides, you get 1 minus u is negative e to the negative y. So 1 minus u is negative e to the negative y. Yeah, there are a lot of ways you can simplify this a little more, but that's fine. I'm going to leave it like that. So I'm going to erase a lot of the board, and I'm going to write this equals this. So just, now again, we're going to take both sides as powers of e to get rid of the ln. So e to this equals e to this. And remember a trick with the c. When you have a plus c in the power for e, you can write it as times e to that, and then replace that with just c because it's a constant. Good. E to the ln's cancel, and you just get 1 plus e to the negative y over negative e to the negative y on the left. On the right, they kind of cancel, but you'd have to write this as all to the negative 1 power. To get e and ln right next to each other, we need to get rid of the negative in front by bringing the negative outside as a whole power, or negative 1. This is, I'm just going to write it as just c, and I'm going to write it in front. So c times e to this, they cancel, so we just get 1 plus cosine of x all to the negative 1. Let's see, so yeah, we get 1 over negative e to the negative y plus e to the negative y over negative e to the negative y. It's a lot to look at. But here you're right, these cancel, you just get negative 1. And here you can bring this e to the negative y power up as e to the positive y. So this is going to be e to the positive y over negative 1. Dividing by negative 1 just makes a negative. On this side, we get c over 1 plus cosine of x. And in fact, you know what we can do? We want to get y by itself. I'm going to multiply both sides by negative 1.
Okay.
Now here, you just get positive, e to the y plus 1. Here, c times negative 1 is still a constant. You can write negative c if you want, but I'm going to reset it as c. If you want, I'll call it c1. So c1 is negative c. Okay? So then subtract 1 to the other side. And then take both sides, take ln of both sides. So we get y is equal to ln of c1 over 1 plus cosine of x, all minus 1. And then we can use our initial condition to find c1. So y of 0 is 1, right?
Mm-hmm.
So y of 0, according to what we found for y, is going to be ln of c1 over 1 plus cosine of 0. We're running out of space here. 1 plus cosine of 0 minus 1. Cosine of 0 is 1. So this is c1 over 2 minus 1. Ln of that. Y of 0 is just 1. So if we take both sides as powers of e to the 1 is equal to e to the ln of this. E and ln cancel out. So we get e is equal to c1 over 2 minus 1. If we add 1 to the other side, we get e plus 1 is equal to c1 over 2. If we multiply by 2, we get 2e plus 2 is equal to c1. By multiplying both sides by 2. Distributing, we get 2 times this plus 2 times that. So that's this. Good. So now, in total, our answer is y is ln of c1, which is 2e plus 2, over 1 plus cosine of x minus 1. There we go. If you factor out an x here, you get 1 minus t plus x times 1 minus t. So if you pull a 1 minus t out, you get 1 minus t times 1 plus x. So you can actually, by grouping, you can factor this and then just separate variables like that and do by separable. I'm not going to do it like that, though. I'm going to actually do it by integrating factor. But I'm just mentioning that you could do it by separable if you wanted to. So to do it by integrating factor, we need to, well, our function is x, so I need to bring all x's to this side. And I'm going to write this as x prime. So this is x prime. Subtracting these to this side, or I guess bringing them to this side by subtracting and adding, we get negative x plus tx is equal to 1 minus t. Good?
Okay.
Now these two have an x in common, so I'll pull x out. So it's x prime plus something times x. It's going to be negative 1 plus t. So far, so good, I think. So if you take a look at what this looks like, we want to use an integrating factor, and it is of the correct form. We have p of t and q of t. We're used to y's and x's, not x's and t's, but still we can apply an integrating factor. So to apply the integrating factor, we need to first find I of t. So there's like 2 steps to this process. The first step is find I of t. And that's e to the integral of p of t dt. And p of t is negative 1 plus t. So I'll write it like this. And let's see. Antiderivative of negative 1 is negative t. Antiderivative of t squared is 1/2. I said that funny. Antiderivative of t is 1/2 t squared is what I meant to say. Okay, so I hope that's okay. The next thing is, well, once we have I of t established, which we do, that's I of t, there's not really much you can do here to simplify this. It's kind of stuck. The second step is to use the formula. X is equal to 1 over I of t times the integral of I of t times q of t. If you remember that. So it's going to be 1 over e to this times the integral of this times q of t. Now I'm looking at this integral, and what it's screaming out to me is u sub, because our power of e is some crazy expression. So I'm going to try to let the power be u and see if this catches that. I'm going to write this as e to the negative this power. If you distribute the negative, then you get e to the t minus 1/2 t squared. It's just less to write. It looks a little easier in the eyes. So it's t minus 1/2 t squared. Basically just negate the power to bring it up on top. Times the integral of 1 minus t e to the negative t plus 1/2 t squared dt. And I said we're going to try to use a u sub on. So if u is the power, negative t plus 1/2 t squared, then du is negative 1 plus t. Perfect. Dt times dt. Why is that perfect? Because negative 1 plus t is just t minus 1, and there it is. So negative 1 minus, or 1 minus t. Oh, you know what? It's not the same. It's not the same. It's almost the same, though. If you pull out a negative 1, then du is, let's do this. If you multiply both sides by negative 1, you get 1 minus t dt. There we go. So 1 minus t dt is not du quite, but it's close. It's negative du. Okay, so we can make the whole thing negative now. So we can replace 1 minus t times dt by negative du. So it's negative this. Integral of, we don't need 1 minus t dt anymore. That's replaced with negative du. But we already pulled out a negative, so that's fine. We have negative du right here. And now what we have left is, don't write this, e to this is just u. So it's e to the u. Antiderivative of e to the u is itself plus c, but u was just this. So it's e to the negative t plus 1/2 t squared. Good. So now, when you distribute this, negative e to the t minus 1/2 t squared, what happens? Well, the first two will cancel out because the powers are opposite, actually. Notice you add the powers, t minus t is 0. Negative 1/2 t squared plus 1/2 t squared is also 0. So you get e to the 0, which is 1. In fact, it's negative 1. And then we would get minus c, e to the t minus 1/2 t squared. This is x. At this point, we can actually use our initial condition. We're basically done here. So now we can, let's apply our initial condition now. Let's say over here. Actually, I have space over here, don't I? So so x of -1, replace all t's with -1s. We get -1 plus, so -1 plus c, minus c, sorry, minus c times e to the,
-1.
Yeah, good. So -1 minus 1/2 times -1 squared. Okay. X of -1 is -2. This is going to be -1 minus 1/2. Because -1 squared is 1, so it's -1/2 times 1 is just -1/2. -1 minus 1/2 is -3/2. So we end up getting this. This is a little bit of a mess, but if you add 1 to the other side, it's not too bad, I guess. You get -1 is equal to -c e to the -3/2. Okay, so multiplying both sides by -1 will give you +1 is equal to c e to the -3/2. Then multiplying both sides by e to the +3/2 will actually cancel this out. Because when you add the powers, you get e to the 0, which is 1. So c is e to the 3/2. Okay, so x as a function of t now is -1 minus e to the 3/2 times e to this. But since they both have the same base e, I'll just add the powers and get t. Let me write it like this. 3/2 plus t minus 1/2 t squared. Because if you subtract this to the other side, you get x minus 3xy. And if you pull out an x, you get this. 1 minus 3y. So in this case, you can actually separate by dividing by this and multiplying by dx. So if you want to try it by separable, it's doable. You can try that on your own if you want. I'm not, though. I'm going to use an integrating factor. And since I'm using an integrating factor, I don't like dy dx. I like y prime. Also, I'm missing my initial condition. What was the initial condition? Y of 1 equals 5?
1 equals 5.
Good. So there are 2 steps in integrating factor problems. The first step is to find the integrating factor itself, and that's e to the integral of p of x. Here, p of x is 3x, q of x is just x. Good. So it's e to the integral of 3x dx. Antiderivative of 3x is 3x squared over 2. Because you add 1 to the power and divide by the new power. Since the power is 1, adding 1 to the power is 2, dividing by the new power is just that. And remember, for integrating factor, you don't need to write plus c inside of the power of e. Good. The second step is to use the formula y is equal to 1 over I of x times the integral of I of x times q of x dx. So that's 1 over I. 1 over e to something is just e to that negative power. So e to the negative 3 over 2x squared, let's say. Is that right? Okay. Integral of I of x times q of x. I of x times q of x is just x outside of e to the 3/2 x squared. Which is, again, a u sub problem. Because what if u is the inside? Or the power. If u is the power, then derivative of that is just 3x, and there's an x to catch that 3x.
Yeah.
So if we let u equal 3/2 x squared, then du is just 3x dx. There's our dx, or x dx right there. So dividing by 3, 1/3 du is equal to x dx. So now we can just replace x and dx with 1/3 du. 1/3 is a constant, we can pull it out. Now x and dx are gone. They're replaced with 1/3 du, so there's du, the 1/3 we pulled out. E to the 3/2 x squared, well 3/2 x squared is u, so this is e to the u. And antiderivative of e to the u is itself. So it's e to the u plus c. Much like we saw in the previous example, what's e to the u? Well, u is 3/2 x squared, so this is e to the 3/2 x squared. This is super similar to the previous problem if you think about it. Because what happened in the previous problem, distributing this, happens here as well.
Yeah.
See that? These cancel because they have opposite powers. So what we get after the distribution for the first term is just 1/3. And for the second one, we get 1/3 c e to the negative 3/2 x squared. And that's all equal to y. Now, if you want, I don't know if I'm going to do it, but if you want, you can actually call this c. Because 1/3 times a constant is just a constant. In fact, I will do that. Maybe we don't have to. Well, that's fine. I'll do that. So now let me apply our initial condition now. Y of 1 is equal to 5. So y of 1, this is y of x. So y of 1 is 1/3 plus c e to the negative 3/2. Because when you plug in 1 for x, 1 squared is 1, so the power is just negative 3/2. Good? It's almost the same problem. Jeez, it's like super similar. Okay. Y of 1 is 5, so that's 5 is equal to 1/3 plus c e to the negative 3/2. Subtract 1/3. And then multiply both sides by e to the positive 3/2 to get rid of the negative 3/2 power. Like that. So here they cancel, you just get c. And here, let's see, 5 minus 1/3 is 4 2/3. 4 2/3 is 12 plus 2, 14/3.
Yeah.
So it's 14/3 e to the 3/2. Altogether, we get y now is equal to 1/3 plus 14/3 e to the negative 3/2 x squared. Okay, there was a slight mistake. So we found c was this for number 10. We saw that c was this, and when you plug it in, there's something I missed. So we had y was equal to 1/3 plus 14/3 e to the, and then I wrote negative 3/2 x squared, but it's 14/3 e to the 3/2, then times this. Now the good news is that they combine because they both have the base e, so it's 1/3 plus 14/3 e to the, then add these powers, you get 3/2 minus 3/2 x squared, and this should actually be the final answer. So sorry about that little mistake there.